Hello everyone and welcome. I'm Pubali does Sarkar, and today I'll be guiding you through an exciting presentation on cues. This is the first slide, which is our cover slide. Here you see the title, Q, and my name along with my department, Computer Science and Engineering. Over the course of this presentation, we'll explore what cues are, how they work, and their importance in computing. I'm looking forward to sharing this with you, so let's get started. Today's discussion will cover several important aspects of cues, starting with the basic principles that define how they work. Then, we'll look into how cues operate in practice, including their behavior and the key concepts like enqueue and dequeue. We'll also explore how cues can be implemented using arrays, which is a straightforward approach, and using linked lists, which provides more flexibility. Finally, we'll examine some common applications of cues in real-world scenarios, highlighting their usefulness in managing data and processes efficiently. Throughout this presentation, understanding these core ideas will help you grasp how cues are fundamental structures in computer science and programming. Let's talk about the basic idea behind a queue. A queue is an abstract data structure, and it's somewhat similar to a stack. However, the key difference is that, unlike a stack, a queue is open at both ends. One end is always used to insert data, which we call enqueue. The other end is used to remove data, known as dequeue. This setup reflects the idea of a line or queue in everyday life, where people join at one end and leave from the other. Understanding this fundamental concept helps us see how queues function and why they are useful in various applications, especially when managing processes in a specific order. Let's take a closer look at queue representation. Just like stacks, queues can also be implemented using various data structures. These include arrays, which are simple and easy to work with. We also have linked lists, which offer dynamic memory allocation, making the queue more flexible. Pointers play a crucial role here, especially when working with linked lists, as they help us keep track of the front and rear of the queue. And of course, structures are used to organize the data efficiently. The key point to remember is that the choice of implementation depends on the specific application and performance requirements. Understanding these different methods helps us optimize how queues are used in real-world scenarios, connecting to the overall theme of data structure efficiency and flexibility. Let's take a closer look at the concept of a queue. A queue is a fundamental data structure, and understanding its operations is key to using it effectively. First, we have enqueue, which is the process of adding an element to the end of the queue. Think of it like standing in line at a store. You join the back of the line. Next is create, which refers to initializing a new, empty queue ready for use. Then there's dequeue, which is removing an element from the front of the queue, like being served at the counter and moving on. The size operation tells us how many elements are currently in the queue, giving us a quick sense of its length. And finally, isempty helps us check if the queue is empty, which is useful before trying to dequeue or perform other operations. These functions form the core interactions with a queue, and mastering them is essential for managing data in a first-in, first-out manner, which is common in many applications like scheduling or buffering. Let's take a look at the key functions used to manage our queue. First, we have the enqueue function, which allows us to insert an element into the queue. Think of it as adding a new item at the end, following the first-in, first-out principle. Next is the dequeue function, which removes an element from the front of the queue, ensuring that the earliest added item is always removed first. The create function is essential because it initializes a new queue, giving us a fresh structure to work with. Then, we have the isempty function, which helps us check whether the queue is empty, crucial for avoiding errors when trying to dequeue from an empty queue. Finally, the size function tells us how many elements are currently in the queue, providing insight into its current state. Remember, in this context, we're assuming the queue contains integer elements. And also note, the slide mentions FIFO, which stands for first in, first out. This is the core behavior of our queue. It's important to understand these functions because they form the foundation of how we manipulate and interact with queues in our programs. Welcome to Lecture 0, brought to you by D. Samantha. Today, we're going to explore how to implement a queue using a linked list. Now, queues are fundamental data structures that follow the FIFO principle, first in, first out. To efficiently manage this, linked lists are a great choice because they allow dynamic memory allocation, meaning we can grow or shrink our queue as needed without worrying about predefining its size. When we use a linked list for a queue, we typically maintain pointers to both the front and rear nodes. The front pointer helps us access the element that has been in the queue the longest, which is essential for dequeue operations. The rear pointer allows us to add new elements efficiently at the end without traversing the entire list. One of the key advantages here is that in-queue and dequeue operations can be performed in constant time. Because we're just updating a few pointers rather than traversing the entire list. This makes linked list-based queues very efficient, especially when dealing with dynamic data where the size frequently changes. Throughout this presentation, we'll see how this implementation aligns with our overall goal of understanding efficient data management and manipulation. Using a linked list for a queue is a perfect example of leveraging the flexibility of linked data structures to create efficient, real-world applications. All right, let's dive into the basic idea behind this concept. The goal here is to create a linked list that allows us to efficiently add items at one end and remove them from the other. This structure is often called a queue, and it's really useful when you need to process data in a first-in, first-out manner. To manage this, we'll maintain two pointers, one pointing to the front of the list, which is where elements will be deleted, and another pointing to the rear, where new elements will be inserted. This way, we can easily keep track of where to add new items and where to remove old ones, making the process smooth and efficient. It's a simple but powerful idea that underpins many real-world systems, from task scheduling to data streaming. Throughout this presentation, we'll see how this basic structure can be adapted and utilized in various applications. All right, let's take a closer look at this slide. Here, we're focusing on the concepts of front and rear in the context of a queue. The front represents the point where elements are removed or dequeued, which is essentially the first-in, first-out principle. The rear, on the other hand, is where new elements are added or enqueued. Now, when we talk about a queue implemented as a linked list structure, these concepts become even more important. In a linked list, each node points to the next, and maintaining the front and rear pointers allows us to efficiently add and remove elements without traversing the entire list. This setup is crucial because it ensures that in-queue and dequeue operations are performed in constant time, which is one of the main advantages of using linked lists for queues. Remember, the in-queue operation adds an element at the rear, and the dequeue operation removes an element from the front, maintaining the FIFO order. So, understanding how front and rear work in this structure helps us grasp how queues function efficiently under the hood. It also ties back to the overall theme of data structure optimization, making sure our operations are as fast and resource-friendly as possible. All right, let's take a closer look at this slide. Here, we see the terms front and rear, which are crucial for understanding how a queue operates. The front is where we remove elements, and the rear is where we add new ones. Now, when we talk about dequeue, we're referring to the process of removing an element from the front of the queue. It's a fundamental operation that keeps the queue functioning properly. Moving on, the slide highlights that our queue is implemented using a linked list structure. This is important because linked lists provide dynamic memory allocation, which makes queues more flexible and efficient, especially when the size isn't fixed. Unlike arrays, linked lists don't require us to predefine the size, allowing the queue to grow or shrink as needed. Overall, understanding how queues are built using linked lists helps us grasp how they can be efficiently managed in real-world applications, from scheduling to resource management. And recognizing the roles of front and rear ensures we can visualize how elements move through the queue during in-queue and dequeue operations. Let's take a closer look at how we can implement a queue using a linked list. Here, we define a node structure, queueNode, which contains an integer value and a pointer to the next node. This setup allows us to create a chain of nodes, which is the foundation of our linked list. Next, we define the queue's structure itself, which holds pointers to the front and rear of the queue, making it easy to keep track of where to enqueue and dequeue elements. In the enqueue function, we dynamically allocate memory for a new node, assign the element to its value, and then link it into the front of the queue. Notice how we set the new node's next pointer to the current front, effectively inserting it at the beginning. This method highlights the flexibility of linked lists for queue implementation, especially since it allows us to efficiently add elements without shifting existing ones, unlike array-based queues. Connecting this to our overall theme, understanding linked list implementations of queues helps us appreciate their dynamic nature and how they adapt to different data handling needs. Let's go through this example of implementing a queue using a linked list. First, we have a function called size, which helps us determine how many elements are in the queue. It works by creating a temporary pointer, Q1, starting at the front of the queue, and then traversing through each node until it reaches the end. Each step, it moves to the next node and increments the count. When Q1 becomes null, we've reached the end, and the count reflects the total number of elements. Next, there's the peek function. This function allows us to look at the last element in the queue without removing it. We start again with a temporary pointer, Q1, at the front of the queue. We traverse until Q1 next is null, which indicates that Q1 is pointing to the last node. The function then returns the value stored in that node. Finally, we have the dequeue function, which removes the last element from the queue. Similar to peek, we start at the front with Q1 and keep track of the previous node as we move along. When Q1 reaches the last node, we store its value, then set the previous node's next pointer to null to remove the last node from the list. We free the memory allocated for that node and return the stored value. This example highlights how linked lists can effectively implement queue operations, especially when dealing with dynamic memory. Understanding these functions helps us grasp how queues can be managed efficiently in real-world applications, tying back to the broader theme of data structures and their practical use. Let's take a closer look at the problem with array implementation for queues. The key issue here is that the size of the queue isn't fixed. It actually depends on the number of elements, as well as the order in which we perform enqueue and dequeue operations. Sometimes, even if there's enough memory available, we might find that enqueue operations are no longer possible. This can happen because the front and rear pointers move around as we add or remove elements. For example, after several dequeue operations, the front might move forward, leaving unused space at the beginning of the array. This leads to a situation where the effective storage area for the queue gets reduced, even though memory isn't fully utilized. Imagine the front pointer moving forward and the rear at the end, but we can't enqueue more elements because the array appears full, despite there being free space at the start. To address this, we introduce the concept of circular array indexing. Instead of moving the front and rear pointers linearly, we treat the array as circular. When the rear reaches the end, it wraps around to the beginning, utilizing all available space efficiently. Think of it as connecting the ends of the array in a circle, so the queue can reuse the space that was freed up by dequeues. This way, we make the storage area much more efficient, preventing unnecessary limitations and making better use of the memory available. Let's take a look at some of the practical applications of queues. First, there are direct applications, which are quite common in everyday scenarios. For example, waiting lists for services or appointments are a classic example. People line up and are served in the order they arrived. Another example is access to shared resources, like a printer in an office. When multiple users send print jobs, the printer processes these jobs in a queue, ensuring fair and orderly access. Multiprogramming is also a key application, where multiple programs are managed by the operating system, often using queues to schedule tasks efficiently. Now, moving on to indirect applications. Queues serve as essential auxiliary data structures within algorithms, helping to manage the flow of data and control processes. They are also fundamental components of other data structures, such as graphs and trees, enabling efficient traversal and manipulation. Recognizing these applications helps us understand how cues are deeply integrated into both everyday systems and complex computational processes, reinforcing their importance in the broader context of computer science.